but it's still going to be a quote-unquote improper integral. And that's because there's a vertical asymptote. Well, there's at two locations. The one that's relevant is when x is equal to 2. All right. So if you were to graph this, you're looking at a vertical asymptote as x approaches 2, specifically from the left-hand side. So we'll cross that bridge in a minute. Bottom line is it means that just plugging in a 0 and a 2 isn't necessarily going to be the way to go. All right. So, but we'll get to that. Let's rewrite it, replacing the 2, because that's where the vertical asymptote is. We'll replace that with an a, and we'll write the limit as x approaches a from the left-hand side, right? And that's because it's maxing out at a value of 2. There's no right-hand side to this graph, right? If it's going to approach 2, it's going to approach 2 from the left, right? Of the integral from 0 to a of x plus 1 over the root of 4 minus x squared dx. All right, that sounds good. So, as far as the antiderivative is concerned, you could go with a trig substitution if you want. You could also break it up by the plus sign, one of those integration techniques that we talked about in the last unit. So if I break it up by the plus sign, we'll worry about the limit later on. I would get this. The first part is a U-Substitution component. The second part is an inverse trig component. Right? So let's tackle the U-sub part first. So if U is equal to 4 minus x squared, then du would be equal to negative 2x dx. I just want an x dx, so I'd write it as negative 1/2 du equals x dx. So that would clean up, oh, that's not supposed to be an a, 0 to a, negative 1/2 du over the root of u, which cleans further, and you can skip whatever steps you need to. It cleans further into negative 1/2 u to the negative 1/2 du. The other part we'll worry about in a sec. All right, so that's another bridge we'll have to cross. But this is reverse power rule. So increase the exponent by 1, you get u to the 1/2. Divide by the new exponent, you get a negative 1. All right, reverse substitute. Unless you want to change your bounds, changing the bounds would introduce a new upper bound of 4 minus a squared. I mean, it's ugly. We'll have to deal with that at some point, but I don't want to deal with it right now. So I'm going to reverse substitute, make it negative 4 minus x squared to the 1/2. And that's happening over the interval of 0 to a. All right, so that's the first part. I mean, we can clean it up a little bit further. I mean, we're going to have to do all this eventually anyway, so no time like the present. Negative 4 minus a squared to the 1/2 minus a negative, so plus 4 to the 1/2, so plus 2. Just double checking. Plug in a 0, you get 4, yeah, the 1/2 will equal to 2. All right, so that part's accounted for. We'll apply limits later on, but what we have to do now is tackle the other component. The other part, if you know the shortcut rules for inverse trig functions, you can get this pretty quickly. The antiderivative is actually arc sine of x over 2. And that's by rule on the interval of 0 to a. All right, so that's one of those shortcut rules that kind of saves you from having to do trig substitution, and I recommended that would be something that you research. So, I mean, I can give you this variation of it, but you should definitely research the other ones. If you have a rule, you have the antiderivative of 1 over the root of a squared minus u squared du. It's going to be the arc sine of u over a plus c. Plus c went off the grid. Dang it. Get back. Alright. There's more. There's one for arc tangent and one for arc secant, so definitely worth your time because it saves you from having to do a trig substitution. Okay. Now when we plug this in, plug in the a, you're going to get arc sine of a over 2 minus arc sine of 0 over 2. So this just becomes arc sine of a over 2 because arc sine of 0 is just 0. So we have our antiderivative. It just doesn't seem to advance the plot very much here. Because now we have to find the limit I wrote x approaches it. That's a Monday evening mistake. That's actually a Monday morning mistake. I'm just making it in the evening. It should be, sorry, a approaches 2 from the left. That was bonkers. So limit. Otherwise, that would have been the answer, and we would have called it a day. Maybe we want that to be the case. I don't know. So the limit of all this stuff. Now, whether you're coming from the left or from the right, if it's a constant, you plug in the constant and see what happens. All right? If it ends up giving you a clean calculation, then you're done. The issue is it gives us a clean calculation for only part of it. All right? So I could rewrite this as the limit. By limit rules, the limit of the sum is the sum of the limits. So limit as a approaches 2 from the left, negative 4 minus a squared to the 1/2, that's one part, plus the limit. It's a lot to write, but it's worth writing it the one time to just sort of prove the point of the 2. So we have the 3 components, this guy, and this guy. All right. So if I plug in a 2 for a, 4 minus 2 squared, 4 minus 4, 0, right? So this part here zeroes out. Plus the limit of a constant is the constant. Plus all of that to get to the point. That was your question, right? Like this part? Oh, you did. But in any event, it's going to get you to a point where you have to evaluate an inverse trig function. Okay, so what you can do, there's a few ways to handle it, but those ways boil down to a graphical approach. You're not always, I mean, in the first unit, we used it all the time. After that, it's like hit or miss as to when we're able to use it. See what happens first and foremost, if you plug in a 2. That's arc sine of 1. Just make sure you're in the right mode, radian mode. 1.57. That's half of pi. Yeah, the result of an arc, sine, arc, cosine, arc, whatever, is going to be some variation of pi. It's just sometimes it's so buried that it's hard to get it into the appropriate form. But if you know that it's going to be some multiple of pi, divide out the pi. Oh, 0.5. 0.5 multiplied by the pi. So plus pi over 2. That's 1/2 of pi. So our final answer would be 2 plus pi over 2. Graphically, though, pop in your function, arc sine, second sine. I'll put it in as x over 2. Do a zoom trig, zoom 7. See where it's going as you approach 2 from the left-hand side. Because you can't approach it from the right because it's outside of the domain. But as you approach from the left, it does appear to be increasing. It seems to be cut off here. So maybe, I don't know, like 1.5, 2.5. It's kind of hard to tell. It depends on what the scale is. So my x scale is in units of pi. Sorry, pi over 2. So that's a single pi over 2 right here for x. I don't know if that's something that we want. All right, maybe you change the window, but we're approaching 2. Okay, so as we're approaching 2, we want to know where it's going in terms of y. So you can adjust your table settings to make it start at 2 and have some infinitesimal change in table surrounding that 2. And then take a look at your picture. Or not your picture, your table. And you can see as you're approaching 2 from the left-hand side, it's closing in on about 1.57. All right, so you can get it that way also. So, you know, there's a bunch of different ways you can get it. Most often, they involve your calculator. Yeah, just that part, yeah. All right, so I think that deserves its own video. So page 52, number 7.